All right, you guys, welcome back from our little AP lecture hiatus. We're back in the normal cycle, though, and this is lecture number 1, dealing with population, and our primary focus this go-around is going to be on math involved. We're introducing this right out of the gate, and we'll do lots of practice with this stuff throughout this unit. But here it goes. So, first of all, population ecology. It's a study of populations and why their numbers change over time. We did some brainstorming in class about immigration and emigration and births and deaths and so on, and how those things contribute to a population, which is important for our math piece. It is worth pointing out, though, already that there are lots of other factors within the realm of ecology that we're also going to need to focus on. We'll be getting to those later, but just kind of have that on the radar, okay? And a reminder of vocabulary, of course, is that when we talk about a population, we're talking about a group of individuals of the same species that live in the same geographic area at the same time. All right, so a population of humans just kind of depends on which geographic area we're talking about. We can talk about the population of Walla Walla or the population of Washington State, population of Pacific Northwest, all the way up to the global level. It just kind of depends on how big of an area we want to talk about at a time. But it is important that we're talking about the same species in the same area at the same time. All right? So let's jump right into the math piece here. Population density. This pretty simple term, and I'm going to assume you guys could probably figure out how to do this without a whole lot of instruction. But it's simply the number of individuals of a species per unit area or volume at a given time. All right? Now, sometimes we refer to population over a volume instead of an area when we're talking about aquatic populations. So if we're talking about the amount of plankton and a certain amount of water, we would refer to our water as a volume, cubic centimeters or liters or something like that, as opposed to just a simple area. All right? And it's just simply done by calculating the population divided by the area or divided by the volume. All right? So these two ovals here, as an example, have the same population, but different population density. So if you have a smaller area, that's going to probably cause our population density to increase. So, calculation. We have an example. The United States has a population of about 299.1 million people. That was as of a couple years ago anyways. I'm not sure exactly what it is at the moment. The area of the United States is 3,717,796 square miles. So to figure out that density, the population density, we would take the population of people, all right, divided by the area, and we get about 80.5 people per square mile. And yes, when you do population density questions, you need to include the appropriate units. So if that was an aquatic population, like I said, we would include the volume. If it's a terrestrial population, we would include the area. And that could be square miles, square feet, square kilometers, whatever, as long as you have the correct area measurement with people or minnows or flies or whatever. All right? Now, the kicker, though, the primary focus of our math here is to calculate changes in population size. If we're talking about a global population, for example, there'd essentially be two factors. We'd have births, which is the number of babies, and the deaths, which is the number of people that die. All right? With our global population, we're not too concerned about immigration and emigration, despite science fiction, right? We don't have a whole lot of people or organisms immigrating to Earth from other planets, nor do we have people leaving the Earth directly. All right? So if we're talking about a global population, it's really just births and deaths we're concerned with. When we're talking about local populations, though, where immigration and emigration can happen, we do add a little complexity, although not much. All right? So we have to worry about both births and immigration, and then both deaths and emigration as part of that factor by which our population increases or decreases. All right? So growth rate. So that little r stands for rate. And we can express rate in several different ways. But here's a basic equation. And because it's adding and subtracting in the beginning part of this equation, it doesn't really matter what order you do that in. I just like to write it like this because Births and deaths are related. So take the number of births, subtract the number of deaths. That gives us the growth affected by births and deaths. And then we need to add the net migration, which is the immigration, subtracted from that the emigration. Okay, that's just going to give us a number, a whole number actually. And then we divide that by the starting population, and that will give us our rate. And that rate would be expressed as a decimal at that point. All right, so rate to a decimal, and converting that to a percent and then to a per 1,000. I'll show you guys how to do that in a little bit. But that rate using this equation is our decimal rate. And it might need to be converted depending on the what the question's asking and how we want to express that rate. All right, so population math, finding birth and death rates. Sometimes in population ecology, we want to just know accrued birth rate or accrued death rate. All right, so that simplifies our equation in that we just need to know the number of births divided by the starting population. All right, birth rate is often indicated as a per 1,000 as opposed to a percent or a decimal. That's just really common way to express things in demography. I'm not entirely sure why, but that's the way they do things. But I want you guys to know that it's a very, very simple conversion. All right, so here's our decimal. Right, so the simple division gives us our decimal. All right, now to go from a decimal to a birth rate, okay, as a percentage, we just move the decimal 2 places. Right. Okay, so we get our decimal rate, which is our simple division problem. Right. To express that rate as a percent, we move our decimal 2 places to the right. If we want to express it as a per 1,000, it's 3 places. As you can see, so 0.025, if I move that 2 places, I get 2.5. If I move it 3 places, I get 25. All right, so I want you guys to get comfortable with both of those. We could do death rate in the exact same way. All right, you take your number of deaths divided by your starting population. That gives you the decimal rate. To convert that to a percent, you move the decimal 2 places, which will give us 1.8% in this case. And as a per 1,000, we move 1 more place to get 18. All right, so death rate is just deaths divided by starting population. Birth rate is births divided by starting population. Population growth rate takes into account all those factors, births, deaths, immigration, and emigration. Then dividing by the starting population. All right, and on our starting practice sheets, I'll let you guys use those formulas. All right, so here's an example of population growth rate, right, of a closed community. So closed community means no immigration or emigration. Okay, so all we worry about is births and deaths there. And here's an example of local population where we are factoring in births, deaths, immigration, and emigration, what it would look like. All right, so notice our starting population is, we're always dividing by that after we have this kind of factored in. Okay, in fact, maybe with order of operations, it's probably best that I should have put parentheses around this number like that. All right, to show that we're actually getting this number of births, deaths, immigration, emigration before we're dividing. So I'm going to apologize for that. I'm going to go back to that slide, fix that. Right here, boom, parentheses around that. So fix that in your notes, okay? To indicate that we need to get that total factor of births, deaths, immigration, and emigration before we divide. All right, I think that messes up our order of operations. And then notice here I can express that rate as a percent, or sorry, as a decimal, or as a percent, or as per 1,000. Now I want you guys, again, practice switching out between those just so that you're comfortable with that come tomorrow, all right? Doubling time, we talked about this in class real quick, but often it's typical for projections to look at doubling time. And the way we figure out doubling time, if we know a growth rate, and of course we have to be assuming that that rate of growth stays constant, All right. Doubling time is essentially an increase by a factor of 2. So the way to figure out how long it's going to take to double something is we use this rule of 70. All right. Now, we have to understand that the reason this works and the reason we have to do it this way is that each year the population is increasing. So if I have a 1% increase, all right, each year I'm taking 1% of a larger number. So it's not just simply at a 1% increase, 100 years to double. It actually comes out to 70 years to double. All right, and the reason the rule of 70 works is we need to take the natural log of 2, which is this ugly number right here. But for the sake of what we do in environmental science, we typically just round that to 0.7. All right, so the 70 in this case then is referring to if I turn 7.7 into a decimal, right? Or sorry, into a percent. So we use the rule of 70 with our percent growth rate. Right? If we decide to leave it in its decimal rate, we just use 0.7. All right, so 0.7 divided by r as a decimal, or 70 divided by r as a percentage. Now make sure you differentiate between how you are expressing your rate. If you're leaving your rate as a decimal, you need to use 0.7. If you convert your rate to a percentage, you need to use 70. All right, it's more typical, at least on the AP test, to see our rates expressed as percents. So we usually use that rule of 70. Okay? So, an example, Brazil has a growth rate of 1.7%. All right? How long will it take for Brazil to double its population? So that's expressed as a percent. So I'm going to use 70. So it's a simple 70 over 1.7, and I should get 41.2 years as a result. Those of you who are familiar with sig figs or confident using those, that we might round that to just 40 years, but don't worry about that for the moment. So about 40 years is how long it's going to take Brazil to double its population, which is not a very long time. 1.7% growth in terms of population is huge. In economics, we wouldn't call 1.7% growth the best. But in population growth, 1.7% is actually pretty rapid growth. All right. So Belgium, right, is a highly developed country, and its growth rate is only 0.1%. In how many years will it take to double its population? So notice that's a decimal, but it's expressed as a percent. So we're talking about a pretty small growth rate in this case. So I would go 70, because that is a percent, over 0.1. All right, and I should get 700 years in this case. About 700 years for Belgium to double its population. So really, really slow growth is what we're talking about in Belgium. All right, projecting future populations. Now I'm going to show you guys actually 2 ways to do this. And they both work just fine. They're actually both accomplishing the same thing. They're just different ways of doing it. But if we want to know what the population might be in the future based on a certain growth rate, we can calculate that, and I'll show you the way we do that. So let's say we have a village in Peru, and it's a small village, 435 people, but it's growing at a rate of 2% per year, which is actually fairly hefty growth. All right, so we want to predict what its population will be in 30 years. Okay, so we're going to apply a 2% growth to a certain population as a fixed growth over a 30-year period. And so what we do is we're going to take our starting population, right? Oftentimes that is referred to as PO, population original. Okay. Now, what I'm going to do is, this is a 2% growth per year. All right. That is going to be expressed as a 1.02. The 1 accounts for that original population. All right. So if I just multiply by 0.02 to the 30, I would end up getting a smaller number over time. All right, we're applying a 2% growth to the original population, so I need to have the 1 here in this case. All right, the 0.02 accounts for the 2% growth rate as a decimal. All right, so Here, I need to return my rate back to its decimal form. So that's what I did. So 2%, move the decimal 2 places left, I end up at 0.02. So 1 accounts for the original population, 0.02 is the 2% growth rate, and the 30 is the number of years in the future that I want to calculate that population. All right? And if I do that, I go 435 times 1.02 to the 30th, I get a population of 788. So I nearly double my population in that relatively short 30-year time span, which shows actually, again, pretty rapid growth, even at just 2% per year. All right? Now, the other way you can solve this is using this equation, let me make that a subscript, PO, which is the original population, times e to the RT. All right? And this is original population. So e is a special function on your calculator. So your calculator would say like e to the x. All right? And e is essentially, by using that e, you're using, again, a natural log function. That accounts for that 1 right there. All right? So that's what the e to the x button does for you, is it takes care of that 1 in that function. Now, the r is my rate. And yes, it still needs to be in its decimal form. And t is the time. So the way that would look with the same equation is I would go 435 times e to the 0.02 times 30. All right, and I would still get that same number, 788, if I did it that way. All right, so both of those equations work. This is the way I was taught once upon a time. This is the way you'll see it probably in most textbooks. They accomplish the same exact thing. It's just a different route of doing so on your calculator is all. All right? So you can pick and choose how you want to do that. And I think that concludes new information. So let's do one example. All right? We got, according to the 2010 census, the projected population for December 2011 in the U.S. was 312 million. All right? Or 3.12 times 10 to the 8th. We are growing at a rate of 0.67% per year. So that's already as a percent, mind you. So we're going to have to convert that back to its decimal rate. What is our projected population for the years 2020, 2050, and 2100? All right? So if you guys have already got notes and you feel like you got this, maybe you can go ahead and hit pause. You don't have to watch this. I'm still going to walk those of you that want to see how this looks through this step. All right? So we have original population is 3.12 times 10 to the 8th. So I'm going to go 3.12 times 10 to the 8th. All right, so that is my original population. Okay, times 1 point. Sorry about that. 1 point. Okay, to account for that original population, I need to adjust my 0.67 to its decimal form. So that's already in percent. So I need to go 1.0067. Okay? Very, very important step, the most commonly forgotten or screwed up step when I give this on a test, is converting percents back to their decimal form. Now, the trick here is we need to identify how many years in the future we're talking about. So this 3.12 times 10 to the 8th is in the year 2011. So in 2020, that would be 9 years in the future. All right? And when I punch this into my calculator, I get 3.31 times 10 to the 8th people. All right? So my projected population would be about 331 million people in the U.S. in the year 2020. So for the year 2050, I would do the same thing, although my exponent, rather than being 9, it would be 39. All right, and for 2100, it would be 89. All right, we plug that in, and we'll see that we do get a pretty big population. All right, I get 4.05 times 10 to the 8th people. And in the year 2100, we get about 5.66 times 10 to the 8th people, or about 566 million, a little over half a billion. So that's a lot of growth in this century. Even at just less than 1% growth rate, we're going to be up 200 million people or more just during this century. It's pretty incredible. All right. That's it. You guys will get time to practice this in class tomorrow. And if you got questions on Wednesday, I will attempt to address those for you. All right? Keep after it.